Welcome back, fellow mitochondriacs, for another episode of Cancer as a Mitochondrial Metabolic Disease. I'm very happy to be back with you today to kind of finish our discussion on the very important and second rate-limiting enzyme, phosphofructokinase, as a part of the enzymatic system that continues the glycolysis process and the Warburg effect. So we have covered quite a bit already with PFK, but just to get ourselves reoriented, we are in the middle of trying to look at glycolysis, okay, this multi-step, multi-enzyme process of taking glucose outside the cell, bringing it inside the cell, and subsequently changing it to a variety of substrates that allows it to be ultimately converted to lactic acid. And then lactic acid will be shuttled outside the cell to create the tumor microenvironment, or the lactic acid tumor microenvironment. So we left off on this slide here, and we were talking about how basically, researchers, ones that are willing to go there, have known that the standard of care is not the way to go. And we have another way, and that way is to attack this from a metabolic perspective. And, Seyfried's not the only one who's been kind of beating this drum for a long time. I mean, let's not forget that Otto Warburg made his discoveries, 100 years ago. So the next slide we're going to talk about is we're going to talk about ways to actually attack this problem, looking at ways to either downregulate or to actually inhibit the enzyme phosphofructokinase. And, we talked about how there are three major human isoforms. There's the PFKP, which stands for platelet. There's the PFKL, which stands for liver. And there's a PFKM that stands for muscle. And it seems that depending on the type of cancer you may have, those subtypes may be more common than other subtypes of cancer. And that's where I think that maybe the next generation of pathology could potentially go is to look at your cancer type instead of a biopsy, looking at genetic abnormalities, which we may or may not care as much about. We look at maybe, okay, what type of GLUT transporter do you have, that brings glucose into the cell? What type of hexokinase, or what type of phosphofructokinase? What type of lactate dehydrogenase or PDK enzyme, or whatever that you have, or like what percent of the metabolism seems to be running off of glucose or glutamine, and then allowing the clinician, the metabolic oncologists, I guess you'd call them, give them a way to understand, how to help the patient based off of their phenotype. Now, what I would say is what I've been reading is that a lot of times when you shut down, let's say hypothetically, your cancer was expressing phosphofructokinase platelet type. Sometimes when you have an inhibitor against that type, or I don't know, hexokinase 2, what will happen is like the cancer cell will actually upregulate the other isoform. And so what I've seen in papers is they'll give an inhibitor for, like, let's say there's two major isoforms. They would give an inhibitor for both, and they'll see that the kind of what they call the I've seen it called like the escape pathway, or the survival pathway is kind of like shut down. So my point is that if we're strategic with these inhibitors, it probably should be where you have maybe like a couple of key enzymes that you would inhibit. And then you would maybe want to have one for each of the two major isoforms that are possible. So that way they can't have any escape. But you would probably strategically pick what we would call the rate limiting enzymes for glycolysis and glutaminolysis. And so for glycolysis, the glucose transporter is huge. Hexokinase is huge, and so is phosphofructokinase, which is what we're talking about today. So this paper is titled Targeting Glucose Metabolism to Suppress Cancer Progression, Progressive Perspective of Anti-Glycolytic Cancer Therapy. And it says here that most solid tumors adapt their heterogeneous microenvironment by depending largely on aerobic glycolysis for energy production, a phenomenon called the Warburg effect, which is a hallmark of cancer. The altered energy metabolism not only provides cancer with the ATP for cellular energy, but also generate essential metabolic intermediates that play a pivotal role for the biosynthesis of macromolecules, aka proteins, carbohydrates, fats, nucleic acids, etc., to support cell proliferation, invasiveness, and chemoresistance. The cellular metabolic reprogramming in cancer is regulated by several oncogenic proteins and tumor suppressors such as hypoxia-inducible factor, MYC, p53, PI3K, AKT, mTOR pathway. A better understanding of the mechanisms involved in the regulation of aerobic glycolysis could help developing glycolytic inhibitors as anti-cancer agents. These metabolic anti-glycolytic agents can be more effective if used in drug combinations to combat cancer. Several preclinical and early clinical studies have shown effectiveness at targeting glycolytic pathway as a therapeutic approach to suppress cancer progression. This review aimed at the present and most recent data as of 2019, right, on the emerging drug candidate targeting enzymes and intermediate involved in glucose metabolism. And you can see here that the anti-glycolytic therapy, like I was saying, would target specific key enzymes along the path. I don't think that we're going to have a quote unquote silver bullet. Okay. Now, if we get one, that'd be pretty awesome. But I just don't think we're going to get one. I think you're going to get a combination of very smartly put together either repurposed medications and drugs or natural nutraceuticals in combination with the ketogenic diet. Because look, this glycolysis process, which is ramped up, 10 to 30x over normal baseline, in a normal cell, in these cancer cells, require glucose. So if you give them a bunch of glucose, yeah, we can block all these enzymes. But like, why give it the glucose to begin with? We know that the rest of our cells are metabolically flexible, which is why the ketogenic diet is the foundation. We're talking about like adding things to the foundation to make it more effective, God willing, of course. Okay, so the next paper is titled Targeting Glucose Metabolism Enzymes in Cancer Treatment, Current and Emerging Strategies. And this is a paper that will probably be referred to over and over again as we go down the line for glycolysis. But this is an excellent paper, and it's very systematic, and it helps us understand the current kind of like treatments that are available, or the current things that are available for kind of like each and every enzyme up along the path of glycolysis, which is pretty cool. Metabolic reprogramming, it says, of glucose provides sufficient energy and raw materials for the proliferation, metastases, and escape of cancer cell, immune escape, of cancer cells, which is enabled by glucose metabolism related enzymes that are abundantly expressed in a broad range of cancers. Therefore, targeting glucose metabolism enzymes has emerged as a promising strategy for anti-cancer drug development. Although several glucose metabolism modulators have been approved for cancer treatment over the years, in recent years, some limitations exist, such as short half-life, poor solubility, and numerous adverse effects. With the rapid development of medicinal chemicals, more advanced and effective glucose metabolism enzyme targeting anti-cancer drugs have been developed. Additionally, several studies have found that some natural products, who would imagine natural products actually being effective? some natural products can suppress cancer progression by regulating glucose metabolism enzymes. In this review, we summarize the mechanisms underlying the reprogramming of glucose metabolism that present enzymes that could serve as therapeutic targets. In addition, we systematically review the existing drugs targeting glucose metabolism enzymes, including small molecule inhibitors and natural products. Finally, the opportunities and challenges for glucose metabolism enzyme targeted anti-cancer drugs are discussed. In conclusion, combining glucose metabolism modulators with conventional anti-cancer drugs may be a promising cancer treatment strategy. So, I was doing some research late last night, and I was working on like the next video, like later this week, and we're going to be talking about an enzyme called PFK-FB, which is an enzyme and its product that completely is responsible for controlling glycolysis and basically allowing the cell to either shift between glycolysis or the PPP, the pentose phosphate pathway. So depending on the needs of the cell, it will either make energy through glycolysis and the Warburg effect, or it will make stuff that it needs, like nucleic acids and redox chemicals and stuff like that. And I was just looking at all the inhibitors or potential inhibitors of just that PFK-FB, which is the next thing we'll talk about. And I was thinking, wow, every single paper talks about blocking enzyme X, let's say PFK-FB or PFK in this case, as being the next thing that we should be doing. The authors will use language like, this should be rapidly added to the standard of care, or this should be highly considered to be added as a standard of care. And it just for me confirms what we already know, because sometimes, we're really out in the weeds. We're talking about a very obscure enzyme in glycolysis called PFK. And it sometimes feels like, wow, how does this all fit together, And it's just very fascinating to me that this is even controversial at this point. There's so many papers, so many authors that are coming to the same conclusion. If you block glucose metabolism here, there's effectiveness. If you block glucose metabolism here, there's effectiveness. Imagine if this somehow got to clinical medicine. I think there would be a paradigm shift. It's just that I think that unfortunately the medical system is too ingrained in what they understand. If you look at most of the papers, they also say, in addition to this should be, added. It's always, there could be a strategy with conventional cancer drugs, right? They want to make sure that they don't go too far out, right? And say, oh, this needs to be the standard of care, and, throw away all the old drugs that are killing your normal cells and giving all these horrible side effects and leading to secondary malignancies. They can't go that far, but they want to, it seems like, in a lot of these papers. Anyways, I'll get back on track. So it says here, in the 1920s, 105 years ago, Otto Warburg first observed that cancer cells tend to metabolize glucose to lactate even in the presence of sufficient oxygen, known as the Warburg effect or aerobic glycolysis, or also known as substrate level phosphorylation by Seyfried's group. By the 1980s, with the application of fluorodeoxyglucose positron emission FDG PET scans, glucose uptake in clinical tissue samples could be imaged, and the Warburg effect was confirmed in almost all cancers. The Warburg effect promotes the glucose uptake of cancer cells in the tumor microenvironment. Further studies have revealed that the tumor growth rate positively correlates with glucose levels, and that high glucose levels in cancer patients are associated with poor prognosis. How well will you do with cancer? The worse, the more positive and higher glucose that's bringing in, the worse these people do with cancer. That is axiomatic at this point. Thus, cancer starvation therapy based on glucose deprivation is emerging as an effective treatment for suppressing tumor growth. For example, the ketogenic diet can inhibit the metabolic proliferation of cancer cells by reducing blood glucose. I put this part in not because I'm trying to like reiterate that the Warburg effect is a thing that Warburg, was 100 years ago. It's that even in these papers, like you find bits of truth, right? And this paper said, well, for example, the ketogenic diet can inhibit metabolic proliferation of cancer cells by reducing blood glucose. How about that? Like, why wouldn't that be the first line treatment? It says later that says extensive studies have confirmed that metabolic reprogramming of glucose, which plays a vital role in the proliferation, invasion, and metastasis of cancer cells, is closely associated with survival of cancer cells. Therefore, metabolic reprogramming of glucose metabolism is considered an essential hallmark of tumor genesis and development. So I pulled this slide because it was cool, but the bottom line is it's saying very similar things that we've talked about in the past. We have a normal cell, we have some amount of, glucose and fructose being brought in through the glycolysis system. And that glycolysis system is going to, put pyruvate, instead of going into lactic acid, it's going to start going into acetyl-CoA, go into the mitochondria and make energy to power the cells. There's going to be some degree of biosynthesis made because obviously we still are turning over normal cells even, but just not to the rate that we would for cancer cells. However, we see like these little tiny thin black lines become very red, right? Very thick and red, because this is what's happening. Mitochondrial energy metabolism is not actually happening in the way that it would under normal physiology. So therefore, we're bringing in a ton of glucose. Fructose is like a salvage pathway to get glucose into the cells and then make not acetyl-CoA, because that process is shut down, but we're making a bunch of lactic acid. And that lactic acid, the more I'm understanding, is that lactic acid has to be brought outside the cell. It's actually not a way. First of all, it is a way to, set up this tumor microenvironment and to allow, cancer to have their external shield system, but it's a necessity, because if lactic acid gets trapped inside the cell, or if the pH drops inside the cell, all of the glycolytic enzymes don't work. So therefore, it will shut itself down. So one strategy, which we'll talk about, will be the blockade of these MCT transporters 1 through 4 here. And these MCT transporters are what's responsible for taking lactate and putting it from inside the cell to outside the cell. But that's for another day. So the next slide that it shows us here is that there are, again, the reason why we'll probably be coming back to this paper over and over again, and there are a couple other papers that are as good or, have similar information that are really good also. But my point is that it's showing all of glycolysis in this paper. It's systematically breaking down in glycolysis, just like we are in this video series, and it's showing what is the inhibitors of that. The issue I have with a lot of these papers is that there is, in a graphic like this, it makes you think that, okay, well, if you don't have 3PO or PFK 115 or PFK 158, which interestingly enough will be in the next video because they actually don't even block PFK. I'll digress. But my point is that you would think that this is all we have, right? And then maybe for, GLUT transporters, we have genistein and apigenin and fluoretin. But like my point is that obviously when you actually search the literature, you can find a ton more stuff. And so this is not an exhaustive, graphic, but it is giving us a picture of what we're effectively trying to do, right? We're trying to use something or things that will block glucose transporters, right? So that way glucose can't get into the cell. Then we're trying to use something or some things that will block hexokinase and its different isoforms, right? So glucose getting converted to glucose 6-phosphate. And then ultimately, once it gets to fructose 6-phosphate, we were trying to block the next rate limiting enzyme called this PFK1, which is what we're talking about in this video. And we're trying to block it from getting to fructose 1,6-biphosphate. So we're systematically trying to go at it kind of like the papers do. But in my opinion, not to toot our own horn here, but I think that we're doing it in even a more comprehensive way than these papers are. So the first thing I wanted to talk about was drugs that potentially could target phosphofructokinase. And it says the second rate limiting enzyme of glycolysis is PFK, which catalyzes the conversion of fructose 6-phosphate P6 F6P to fructose 6,1,6 biphosphate, F26BP. PFK is allosterically activated by adenosine monophosphate, or AMP, as well as fructose 2,6 biphosphate, which is critically important for the next video. PFK can be inhibited by the elevation of F26BP level to sustain cancer growth. I actually think they made a mistake there. I think that they're saying that it's because it even says that it can be activated by F26BP, and it says that it's being inhibited. So it's actually not true. And that also doesn't make sense. If you inhibit PFK, you would not sustain cancer growth. So it meant to say activated here. We're doing some peer review here on the fly. F26BP, a product of a reaction catalyzed by the next enzyme that we're going to talk about, which is called PFKFB, is the most potent positive allosteric effector of PFK1. PFK2, FBase2, a bifunctional enzyme responsible for the catalysis of both the synthesis and degradation of F26BP mediated through its N-terminal domain. I'm going to kind of skip some of this stuff. It's not really that important for us. In other words, PFKFB is an enzyme with both kinase and phosphatase activities, and the level of F26BP depends on the relative activities of kinase and phosphatase activities. Therefore, inhibiting the enzyme activity of PFKFB while maintaining its phosphatase activity can inhibit PFK activity by reducing 2,6-BP levels. Okay, let's look at a graph here. So this graph doesn't show it. Give me 1 second. Does this show it? Okay, this does show it. All right, let's zoom in here. Let's go to like 100%. And let's go here. I'll probably have a better graphic later in the talk, but this is what we got at my fingertips this second. So what it's effectively saying, you guys, is that this enzyme, PFKFB, okay, this enzyme here, makes a chemical compound called F26BP. And this F26BP will ramp up. It's actually the strongest known kind of like activator of PFK. Okay, so what they're saying is that another strategy could be to block this enzyme so the amount of F26BP drops and it can't activate PFK. We are going to talk about that strategy in the next video. So I bring this up as kind of a teaser of what we're going to be talking about. In addition, PFKFB is commonly overexpressed in breast, colon, ovarian, and thyroid cancers, but is expressed at low levels in normal tissues, and the basis of targeting therapies for a variety of cancers. So basically, like, if we hit this thing hard, it's not going to really affect the normal cells, even if you're like eating sugar, or not sugar, but you know, if you're eating carbohydrates and you're not fat adapted, you know, which is going to be preferred, because then that way the normal cells are even less reliant on glucose, right, and fructose, and that way we can really hammer potentially this enzyme to have the maximum effect. It was also found that inhibiting PFKFB could suppress pathological angiogenesis without affecting normal blood vessels. So it's saying that it's going to suppress what we'll talk about in the next video is basically that PFKFB is highly associated with the creation of new blood vessels for cancer cells. And so that's what this pathologic angiogenesis is. And when they said it was when it inhibited it, it did not affect the normal vessels. PFK is controlled by a family of bifunctional enzymes called PFKFBs. It just says here that PFKFB3 is overexpressed in a variety of cancers, including breast, colon, nasopharyngeal, pancreatic, gastric, and associated with lymph node metastases and survival. A large number of inhibitors for PFKFB have been reported, including 3PO, PFK15, PFK158, YN, etc. In contrast to 2DG, which can cause serious toxicity and systemic adverse effects, 3PO only partially and transiently reduces glycolysis without causing serious toxicity to normal tissues. Administration of 3PO was shown to produce a rapid reduction in glucose uptake, lactate production, and ATP generation in T cell leukemia cells. So I was thinking to myself, this seems a little bit redundant. Why am I showing this? Well, this particular paragraph is extremely important for a couple different reasons. Number one, here's a myelodysplastic syndrome, right? Here is a non-solid tumor, a T cell leukemia that is being affected by 3PO, and the glucose uptake is being reduced, the lactate production is being reduced, the ATP production is being reduced, excuse me, in a non-solid tumor. So I wanted to show that because it's not often that we get a lot of examples where the Warburg effect and then these metabolic inhibitors are being shown to be or have an effect or be effective for, B cell, T cell, leukemia, lymphomas, etc. So therefore, a lot of people believe, or I would say errantly believe, that the Warburg effect is only affecting solid tumors, and that blocking glucose and being on a ketogenic diet is only going to affect people who have the more common, breast, colon, pancreatic, et cetera, cancers. And that I have not seen that to be true. It seems to be axiomatically true for all cancer. It's a hallmark of cancer. That's why they keep saying it over and over again. It's seen in most cancers, et cetera. It's just that there isn't a lot of published studies that I've seen, because I go through a lot of papers. I haven't seen a lot of papers where they talk about, trying, I don't know, EGCG or quercetin or 3PO, on a non-solid tumor. So therefore, it kind of like gives us like a confirmation bias that like it isn't effective or isn't going to have an effect on these non-solid tumors. But I just like to point those out. So anyways, all right, where were we? Okay, so PFK15, a derivative of 3PO, exhibits approximately a 100-fold increase in the PFK-FB inhibitory activity when compared to 3PO. PFK15 has been reported to exhibit significant anti-cancer activity, reducing 18 FDG uptake and F26BP levels in xenografted tumors. Moreover, PFK15 exhibits pro-apoptotic effects in transformed cancer cells in vivo and in vitro. Several studies have shown the ability of PFK15 and PFK18 to synergize with targeted chemotherapeutic regimens. We'll talk about these. In addition, it's been shown that PFK15 increases the sensitivity of chronic granulocytic leukemia cells to imatinib and enhances cytotoxicity of oxaliplatin against colorectal cancers. The combination of CTLA-4 antibody and PFK1858 could significantly enhance inhibition of cancer growth, showing a bright future for immunotherapy combined with targeting glucose metabolism therapy. And I, as much as I'm not a big fan of using medications and drugs, I do think that the combination of immunotherapy with glucose and glutamine metabolism therapy makes the most sense because, what is the lactic acid and the succinic acid tumor microenvironment, the acidic tumor microenvironment effectively doing? It's shutting off our immune system from being able to kill the cancer cells. It's also effectively shutting off immunotherapies from being functional and chemotherapy from being functional. And it just makes more sense to wake up to our own immune system rather than kind of like kill it off with chemotherapy. So I do think that there is a way forward between kind of like conventional and unconventional medicine. It seems like immunotherapy would be the better choice, but we'll have to see if that pans out. Some studies have found that PFK-FB3 plays a role in the repair of DNA damage caused by homologous recombination, leading to development of small molecule PFK-FB3 inhibitor. I'm not going to try to read that because it's about 15 characters long, suggesting that PFK-FB3 may play a role in the initiation and development of malignant tumors. So it's not that just this like creates a vicious cycle that's feed forwarding the Warburg effect, but it also seems to play a role in initiation of development of cancer to begin with, which I think is interesting. Moreover, compounds such as, I'm not going to try, YZ9, PKP, again, not going to try, benzodoles, and salicylic acid may also have effects, pharmacologic effects on PFK, which is what I finally wanted to get to, which was talking about a couple different things that are going to have effects on PFK from a drug perspective. And I wanted things in particular, of course, that are cheap, safe, well-established, and have effects. So that's why I wanted to talk about salicylic acid. But before I go there, I'm going to talk about 3PO. And I'll be very frank with you, since actually having this slide put here, I'm going to, in real time, take it out. I'm going to put it where it should be. Let's just put it here. Because what I've realized is that 3PO, although it'll be on graphics like we saw here, showing that it blocks PFK, when I did some deeper diving into it, it blocks PFK, it seems like indirectly, through the blockade of that PFK-FB enzyme. And so therefore, which also may not be true, but I'll digress. So my point is that I'm going to take that out of the slide deck for PFK, because it seems like it's an indirect mechanism, whereas I'd like to look at things that actually have more direct mechanisms, either by directly downregulating the enzyme PFK or by having a true inhibition. And that brings us to aspirin, simple salicylic acid, acetylsalicylic acid. And I chuckled a little bit. There was somebody who made a comment and was like, well, that's of course why they push us over to the new drugs. I don't consider ibuprofen new, but the NSAIDs and other things that block the what we call the COX and the LOX enzymes, such as ibuprofen, meloxicam, diclofenac, et cetera, and taking us away from aspirin. And I had to laugh because I was like, you sound about as cynical as I do. But regardless, salicylic acid has actually, and aspirin has actually popped up kind of a couple times during this series. I don't know if you remember, but salicylic acid and aspirin also block glutamine as well. Salicylic acid blocks the SLC7A11 or the XC enzyme or transporter that actually transports glutamate outside the cell and brings cysteine inside the cell. And it's also known as the Achilles heel of the tumor. And that is critically responsible for redox homeostasis. And so therefore, aspirin kind of has multiple roles, because what I was taught, at least when I was in medical school, is that aspirin may have an effect maybe on colon cancer because of the lowered inflammation, because that's how we look at salicylic acid and the similar drugs, is that they lower levels of inflammation through affecting kind of NF kappa B and several cytokine systems, as well as the COX enzymes. So that's how I was always taught it when I was in medical school. And I think that's how it's pretty much thought of as today, is it may have some role in colon cancer just for the inflammation standpoint. But what we're seeing is that it actually has other perspectives that it can do. I had taught on, probably like in January when we were still in the glutamine series, looking at its effects on SLC7A11. But now we're seeing there's an effect also on the glucose side of things as well with PFK. So this paper was published in 2009, which was surprising because they've known about this for a long time, it seems. And it says that the paper is titled Acetylsalicylic Acid and Salicylic Acid Decrease Tumor Cell Viability and Glucose Metabolism by Modulating 6-phosphofructokinase, or PFK1, also known as, structure and activity. And it says the common observation that cancer cells present higher glycolytic rates when compared to control cells leads to the proposal of glycolysis as being a potential target. You see how they're saying like potential target, potential target? They've been talking about potential target for 20 years for the development of anti-tumor agents. Anti-inflammatory drugs such as acetylsalicylic acid, ASA, and salicylic acid, SA, present anti-tumor properties, including apoptosis and altering tumor glucose utilization. The present work aims to evaluating whether ASA could directly decrease cell glycolysis through inhibition of major regulatory enzyme within this pathway, 6-phosphofructokinase or PFK. We show that ASA and SA inhibit purified PFK in a dose-dependent manner. And this inhibition occurs due to the modulation of the enzyme's quaternary structure. ASA and SA promote the dissociation of the enzyme active tetramers into quite inactive dimers, a common regulatory mechanism of this enzyme. So let me stop here for a second because I want to read all of this, but I want to see if I can figure out something that helps us understand what's actually happening. Man, I don't think I have a picture of this. Well, let's use this. So PFK is made up of kind of 4 distinct proteins, okay? And those proteins aggregate into what they call dimers, or 2 proteins that aggregate together. And then when those 2 proteins aggregate together, that's called the quaternary structure of the protein. And what it's saying here is that when the 2 dimers are combined into a tetramer, it's an active enzyme. But when it dissociates into these 2 active dimers, or 2 different proteins that are connected to each other, but they're not together, it's a very inactive enzyme at that point. And it's saying that's a common regulatory mechanism of this enzyme. And what acetylsalicylic acid and salicylic acid is doing, it is taking the active, tetramer and breaking it apart to an inactive form of the enzyme. And it seems to be a pretty effective strategy because the more salicylic acid is given, the less active the enzyme is, as we'll see in these graphs. The inhibitory effects of ASA and SA on PFK are fully reversible and can be prevented or reverted by binding the enzyme with actin filaments. Both drugs are also able to decrease glucose consumption in human breast cancer cell line MCF7, as well as its viability, which decrease parallelly, I don't think I've ever seen that word, to the inhibition of PFK on these cells. In the end, we demonstrate the ability of ASA and SA to directly modulate an important regulatory intracellular enzyme, and propose that this is one of the mechanisms promoting its anti-tumoral effects. So it may have nothing to do with inflammation, but it may have less to do with inflammation. It has also to do with blocking glucose and glutamine, which is exactly what Warburg has been talking. Well, Warburg didn't talk about glutamine, but he talked about glucose for 100 years since his passing, and Seyfried has been talking for a long time too. Because these graphics, it's an older paper, 2009, and I didn't have a lot of room on the slide. So let me just zoom in quickly here to this. And we'll see here that the first one they're looking at here is cell viability. Okay, how many cells are alive? That's actually probably the most important, right? How many of these cancer cells are alive? And then the relative lactate production, okay, is the Warburg effect being shut down, right? Lactate is the end product of the Warburg effect, right? And then relative glucose consumption, and lastly, PFK activity. So we see here that and this is measured in, looks like millimoles. And we have 0, we have obviously 100, and the black is ASA and the gray is SA. And so we see here that as we increase in millimoles they use a max of 10 millimoles of ASA and SA, we see about a 60% decrease in the survivability of the cancer cells. This is, I think, a breast cancer model, if I'm not mistaken, a human breast cancer model. And then they looked at lactate production. You can see lactate production at the higher end of 8 to 10 millimoles just falls off a cliff. I mean, we're talking like 20% of its normal amount made by these cancer cells. Then we look at glucose consumption. We see a less amount there, which makes sense because this is not blocking glucose uptake, and there could be like salvage pathways that are found. Maybe it's maybe it's shunting towards the PPP or something like that. So glucose is maybe still being utilized, but it doesn't really matter, right? Because the bottom line is the cancer cells are actually dying, right? And the lactate is being shut down, so therefore, ultimately, it's not going to be able to take this for a long period of time, likely. Or it's not going to have the uncontrolled growth. It's kind of like what Dr. Seyfried said in one of his papers, in his most recent papers. Although it said something like, although we haven't tested every type of cancer, we have not seen any cancer that has been tested ever have uncontrolled growth that was common to cancer before implementing a ketogenic diet, right? So my point is that although the glucose could be potentially consumed, it's kind of not going to allow uncontrolled growth, because now we're having cell viability issues. We're having lactic acid being decreased. And what we're seeing is that there's also a dose-dependent amount of PDK. So they believe that the reason for salicylic acid, aspirin, basically, having an effect on glycolysis, on lactate production, on cell viability, they believe, is likely mostly related to its effect on this PFK enzyme. I think that is kind of vacuum thinking. I think it probably is the combination of everything. It's going to be, it's going to be its effect on glutamine as well, probably. And that wasn't tested here, and it probably wasn't discovered till later, than 2009, that it had an effect on the glutamine transporter as well. But no matter what, I mean, this is pretty unbelievable that just adding one thing was able to, something that we all probably have in our cupboard right now, right, is going to have an effect. Now, I'm going to make a public statement, right? Like, don't start taking aspirin without talking to somebody, because aspirin can also cause harm, right? Like it can, well, first of all, it inhibits platelet formation or platelet aggregation, so you can bleed more than you normally would, right? But similar to NSAIDs, it can also lead to kind of ulcers and stuff like that. Gastric ulcers potentially could cause, some kidney problems as well because of how it functionally works. So it's not a silver bullet, but I will tell you this, that for some conditions that we treat, for example, I'm gonna have to look at the dosing, give me 1 second. But for pericarditis, we can use massive doses of aspirin. And I only have to look it up because it's not something it's not like this 81 or 325 we give for like strokes and heart attacks and stuff like that, right? It's like mega doses. So pericarditis, maybe a better way to do it is aspirin. Adult dosing. Where is it? It's going to have it here somewhere. Pericarditis, here we go. So look at this, 650 milligrams every 8 hours. So, for most people, they're taking an 81 milligram aspirin a day. They're taking, a 325 at most. And we're talking about like doubling or quadrupling what the normal dose was every 8 hours, right? So we give it for weeks on end. So again, this could be something potentially as either a short press, like a week maybe, or a couple weeks at a time, and then take a couple weeks off. Or it could be like even more like what Dr. Seyfried talked about, having a press be on like HBOT days or IV vitamin C days or something like that. So it's still kind of to be determined. And also I'd have to look at the pharmacokinetics to see how much aspirin it would take, oral aspirin basically, to get to these kind of like serum, micromolar concentrations. But no matter what, it's just pretty exciting that we have things like this at our disposal, and ultra cheap, right? Like aspirin's about the cheapest over the counter, thing you can get from a pharmacologic standpoint, right? Okay, so the next paper I thought was really also pretty cool was basically taking aspirin and dissecting it and what it can do, right? So Aspirin, a well-known non-steroidal anti-inflammatory drug, NSAID, has a recognized role in cancer prevention, as well as evidence to support its use as an adjuvant for cancer treatment. Importantly, there has been an increasing number of studies contributing to the mechanistic understanding of aspirin's anti-tumor effects, and these studies continue to inform the potential clinical use of aspirin, both for the prevention and treatment of cancer. This review focuses on the emerging role of aspirin as a regulator of metabolic reprogramming, an essential hallmark of cancer required to support the increased demand for biosynthetic intermediates needed to sustain proliferation. Cancer cells frequently undergo metabolic rewiring driven by the oncogenic pathways such as hypoxia factor, wingless related integration site, WNT, mammalian target of rapamycin, mTOR, and nuclear factor kappa light chain enhancer of activated B cells, NF-kappa B, which supports the increased proliferation rate as tumors develop and progress. Reviewed here, cellular metabolic reprogramming has been identified as a key mechanism of action of aspirin and include the regulation of key metabolic drivers, the regulation of enzymes involved in glycolysis and glutaminolysis, how about that, and altered nutrient utilization upon aspirin exposure. Importantly, as aspirin treatment exposes metabolic vulnerabilities in tumor cells, there is an opportunity for the use of aspirin in combination with specific metabolic inhibitors, particularly glutaminase inhibitors, aka DON, aka betulinic acid, aka membendazole, currently in clinical trials such as CB839 and IASC 6274 for the treatment of colorectal and potential other cancers. The increasing evidence that aspirin impacts metabolism in cancer cells suggests that aspirin could provide a simple, relatively safe, and cost-effective way to target the important hallmark of cancer. When was this published? 2023. Excitingly, this review highlights the potential role for aspirin in improving the efficacy of new generation of metabolic inhibitors currently undergoing clinical investigation. Heaven forbid we use the old stuff that works and is cheap. We have to develop a new inhibitor, don't we? Okay, so first of all, I guess I forgot to look at the graphic. So aspirin has multiple effects, which is pretty cool. So aspirin, probably some of the more exciting ones that I see here are the blockade of hypoxia-inducible factors, which are critical for maintaining the Warburg effect. It will upregulate glucose and glutamine enzymes and machinery that will allow the Warburg effect to be effectively turned on. And it is a key driver, key driver of cancer metabolism. They also have the WNT, beta-catenin, c-MYC axis here, PI3K, AKT, mTOR, the COX enzymes that we talked about, PGE2, NF-kappa B, and the acetylation of p53, and it's involved in enhancing DNA mismatch repair proteins. So you can see here that it has a lot of effects that it could potentially have on cancer as a whole. But what we're going to be focusing on is the metabolic reprogramming part, because we're going to remain laser focused on treating cancer as a metabolic disease or a mitochondrial metabolic disease, which is why that is the title of Dr. Seyfried's book and why I've titled the series Cancer as a Mitochondrial Metabolic Disease as well. So this is a pretty cool graphic because it's no different than what we've seen dozens of times before, looking at human metabolism from a normal and a pathologic perspective, but it has little tablets of aspirin next to it where it's blocking, which I think is pretty cute, but also pretty cool. So we have GLUT transporters, right? Glucose has to get into the cells. Glucose then get converted rapidly by hexokinase to glucose 6-phosphate. Glucose 6-phosphate can be used to make pyruvate, ultimately lactate, right? Or glucose 6-phosphate can go into the PPP and make nucleotides and proteins and amino acids, and as well as NADPH, which helps with redox homeostasis. And then what's not happening is, because this is not normal physiology, is pyruvate, which would normally get into the mitochondria. It's not shown here, but this is the border of the mitochondria, let's say, where acetyl-CoA is being brought into the TCA cycle and used to make energy through oxphos, but that's not happening because, number one, we have broken mitochondria. Number two, we have an enzyme that's upregulated called PDK1, which is blocking PDH, pyruvate dehydrogenase, and not allowing that to get into the cell. So therefore, it shunts all this pyruvate over to lactate, and the vicious cycle goes round and round. What we're seeing also, which I think is critically important for us to have this perspective, okay? So a lot of people will be like, "Oh, I'm EGFR positive," or I'm HER2 positive, or ER positive, or whatever, right? And I'm not saying those things aren't important. They are important, but how are they important, right? So how is HIF, for example, important? Well, HIF is upregulating all the glycolysis machinery, right? So now we can bring in glucose 30 times more than normal cells and we can process it. It's also upregulating PDK. HIF is also upregulating glutaminolysis pathways as well, right? So it's important because it's upregulating the Warburg effect and the enhanced glutaminolysis seen in the metabolism of cancer cells. That's why it's important. NF-kappa B does the same. NF-kappa B works through HIF. NF-kappa B works through multiple pathways. NF-kappa B does similar things. So does c-MYC. So does mTOR. mTOR works on several pathways. So my point is that the reason why these are important is because they're upregulating the machinery of glycolysis. Now I'm going to skip down that I wasn't expecting to do, but I want to use this as a way to prove this or show this. So why is inflammation in cancer bad? Well, because it works through these pathways. Why is stress bad? Well, because it works through these pathways. Why is progesterone or estrogen? Because if we have ER and PR positive or other sex steroids, depending on the cancer type, let's say prostate cancer with androgen receptors. Why is it bad? Because it works through this process. Why is EGFR and HER2 important? Because of this process. Why is hypoxia or hyperglycemia important in this process? Because it works through this process. All these things that we think are unique to several cancers, okay, are not really unique. They all coalesce at glycolysis and glutaminolysis. It's just the question is, how is it getting there? Is it getting there because we have a ton of, insulin present, and insulin is upregulating, PIK3 AKT and mTOR and all these, and leading to glucose upregulation and utilization? Is it because we have hypoxia or pseudohypoxia, or because we have a bunch of, hormone receptor positive, breast cancer cells, and they're working through MYC, or they're working through, mTOR? Is that how it's working? Maybe. But my point is that it ultimately coalesces at glycolysis, and the breakdown of glucose into lactate and the breakdown of glutamine into succinate and ultimately citrate and other things that make the biosynthetic things that these cancer cells need to develop and grow uncontrollably, right? So my point is, by showing this slide, which is pretty cool, again, because aspirin blocks multiple of these pathways. You can see here, everywhere there's a little aspirin, it blocks these pathways. And you can see here that it's basically all the kind of macro pathways that lead to these glycolysis, issue as well. And what's also cool is that aspirin also blocks PFK1 in a dose-dependent manner as well. So not only does it block kind of the surrounding pathways that drive the Warburg effect, but it also blocks the Warburg effect like at the level of the Warburg effect by blocking PFK. Pretty cool. So the next paper on aspirin is titled "Aspirin Reprograms Colorectal Cancer Cell Metabolism and Sensitizes to Glutaminase Inhibition." Also a fairly recent paper, October 2023. So I'll just say it again. This is not a Seyfried paper, okay? This is like a bunch of other authors that have nothing to do with Seyfried, not in his lab, not in his group. And you're seeing here that they're starting to figure out that what Seyfried has been talking about for a long time, and Warburg, but for a lot longer before him, is that we have to block glucose, okay? When we block glucose, then the cancer cells become more reliant and they upregulate even further their glutamine utilization. And so what happens is that when we give aspirin and we block glucose utilization, and we block a lot of the pathways that upregulate glucose utilization, it sensitizes to glutaminase inhibition, okay, which makes total sense because the two main drivers of cancer metabolism are glucose and glutamine. If you shut down glucose, glutamine will take over and be the driver and allow for at least some level of survivability. If you block glutamine only and you don't block glucose, you're doing the same thing. But if you block both, you're going to have the maximal effect, right? And when you block one, the other one's going to take over. And so, of course, if you block glucose's pathway using aspirin, and then you use something that's going to inhibit glutaminase, which is the major kind of like grand central station of the glutaminolysis pathway, of course, is going to make it more sensitive to those. Of course, like anybody who's been studying Seafried for more than a couple of days would that would make sense. But anyway, we have to prove it. So this paper was published in October of 2023, and I particularly highlighted, we show that aspirin regulates several enzymes and transporters of central carbon metabolism and results in the reduction in glutaminolysis and co-contaminant increase in glucose metabolism, demonstrating the reprogramming nutrient utilization. We show that aspirin causes likely compensatory changes that render the cells sensitive to glutaminase inhibitor CB839. That could also, you could substitute DON, you could use whatever is blocking glutaminase, right? But they're using CB839. Of note, given the clinical interest, treatment with CB839 alone had little or no effect on the colorectal cancer cell growth or survival. Again, in a vacuum, it doesn't make sense. However, in combination with aspirin, CB839 inhibited colorectal cancer cells proliferation and induced apoptosis in vitro, and importantly, reduced crypt proliferation in these mice in vivo. So we see here that glucose and glutamine are being used. When we added aspirin, it shunted metabolism in a way that made cancer cells more sensitive to glutamine inhibition, and therefore it caused this CB839 inhibitor of glutaminase to have much more of an effect, which makes sense. These are just graphs kind of like looking through this. This is a relative cell number. So how many cells are survived, right? So you see the control is they're all alive, right? And then we add this kind of a double graph. So we're seeing increasing amounts of CB839 in micromolar concentrations, 0 to 10, and we see increasing concentrations of aspirin. So if we have 0 CB, okay, let me just use this in a way that makes sense. So if we used some aspirin, okay, basically with 0 glutamine inhibitors, we see a relative, let's say a 18% decrease in cancer cell viability, just adding aspirin at 2 millimoles. If you were to just add aspirin at 4 millimoles, you see about a 20% decrease in cancer cells that are here. However, as you increase the concentration of CB839, the glutamine inhibitor, you see that there is some decrease, okay, but not much. Maybe I would say, it's hard to say because the graphic is difficult, but I would say less than 10% for sure decrease, even at the maximum concentration they're studying of this glutamine inhibitor, right? However, at just 2 millimoles of aspirin, we see a 20% decrease. With 5 millimoles of this glutamine inhibitor. When we increase it to 10 millimoles, we see about a 40% decrease. And then if we use 4 millimoles of aspirin at 5 micromoles of glutaminase inhibitor, we see I would say about a 60% drop. And that goes down to about, I would say 70% drop at 10 millimoles. So my point is that it's a dose-dependent decrease. So as we increase dose of aspirin, it's going to preferentially decrease the amount of glycolysis happening, and it's going to make the cancer cells probably more dose-dependently reliant on glutamine. And then when we block glutamine at dose-dependent levels, we see dose-dependent killing of cancer cells or less relative numbers of cancer cells still alive, which makes total sense because that's how they survive. So I just think it's pretty interesting to see at least some people in the research community kind of wake up to this fact that Dr. Seyfried's been talking about for years and years. But if that means that we get like rapid fast tracking of a paradigm that gets us, stuff that's going to help cancer patients, and that's fantastic, we'll deal with it. It's just that it's not been fast enough for my liking. And I can guarantee you that if your loved one had cancer, or if you have cancer, or if you've lost someone, God forbid, to cancer, then it hasn't happened fast enough for you either. So we see here that relative apoptotic cells, we see that there's, basically, this is a relative number, right? So 1 is like the baseline amount of apoptosis. If we add just the glutamine inhibitor, we see almost nothing. If we add just aspirin, we see, almost a double the amount of apoptotic cells. But look what happened when we add the glucose and aspirin together. We see a 4.5, almost 5-fold increase in apoptosis from these cancer cells just by adding these two products in, which again makes tons of sense. Now, does aspirin work by itself, or can it work in combination with other stuff, like genistein, which is something we talked about kind of heavily during the glutamine transporters? If you remember back, I'm not going to scroll back because it would take too much time, but genistein, I think, genistein and apigenin both were probably the most powerful glucose transport uptake inhibitors. And I don't mean in terms of like dose dependent. I mean more that that the cancer cells, how do I say this? It blocked the maximum amount of glucose transporters. If you remember right, there were about I think 13 different glucose transport isoforms, and genistein and apigenin were it blocked all of them. So my point is that this wouldn't be a bad combination to use, aspirin and genistein. And it says genistein and aspirin combination exerts cytotoxic and anti-migratory effects in human colorectal cancer cells. And this was published in May of 2024. And I didn't necessarily want to read this, but I just wanted to show that this is here, cell viability, right? So you see here that, and this is in millimoles, control, and this is a colorectal cancer cell model. At one millimole, wasn't doing a whole lot. 2.5 of aspirin only. You got, some killing. At 5, we have, a lot. And then at 7.5, we see nearly all of them dead. And then we see here that the fixed rate of ASA for this combination study is 2.5. So, the minimal amount, right? But we see here that when it's combined with genistein, we see a dose-dependent amount of killing by the combination, similar to that of by itself. I mean, genistein by itself has profound effects on these colorectal cancer cells. Let's see here. We see that at 10 millimoles, no effect. 25, some effect. 50, about 50% are dead, and then slightly less. So there's a slight improvement in aspirin to genistein. I would be curious because you obviously see that the massive amount of cancer cell killing happened at 5 and 7.5 millimoles millimoles respectively, and the majority of the cancer killing cells had here at 50 and 75 micromoles of genistein respectively. I would have liked to see them do either 5 or 7.5 plus genistein in increasing amounts, just because I'd love to see it go to 0. It probably would, but we'll have to digress because we don't have that data, but I would guess that it would. So we can see that it's just another touch point that we have to show that these cancer cells have to be attacked in a scientifically logical way. And blocking glucose metabolism at multiple levels makes a ton of sense. And that's what they did here with aspirin and genistein. And we see that the results show it, even at very small concentrations of aspirin. This is another cell type. This is basically a normal cell. And you see here that at maximum concentrations of aspirin, you see basically no cell damage or cell death. Same with genistein and the combination. You see almost no damage to normal cells, which is exactly what we want. We want a drug that's effective against cancer cells specifically, and we want something that doesn't harm the normal cells at all, right? Because we are looking at the Achilles heels, the hallmarks of cancer, of enhanced glucose and glutaminolysis. They did this. I'm guessing this is probably the same group Yeah, the same group. This was in May. This was in July of 2024, where they used Ficitin. And again, this is, I mean, I've seen this flavonoid come up, in our studies, I guess, kind of infrequently, I would say. I would say that if I would pick one, I would probably pick like EGCG, or I'd pick like quercetin or berberine or curcumin or something that we see like over and over and over again. They didn't do that. And I would, you could say that aspirin showed the same effect on these. This was a melanoma model. Basically the same effect at 5 and 7.5 millimolar, concentrations. You see something very similar. They used 2.5, which had probably less of an effect on this model, this melanoma model, than it did in the colorectal cancer cells. But you see that there is a dose dependent, and they kept it at 2.5 again. I wish they would have went to 5 for this subsequent paper, but they did this at 2.5 and then increasing micromolar concentrations of Ficitin. And you see also a decrease, but it's just not as effective as it was seen for the genistein groups and the combinations. And again, the ultimate study would have been to do basically aspirin at a higher millimole amount, plus maybe Ficitin, maybe, I don't know, or some other flavonoid, and then add like that CB839 or DON or something that blocks glutamine, and see where you would get from there. I would guess that would go to near zero. And that's it's just highlighting that combinations are better. Okay. So let's see here. Is this? Yeah. So this is a surprise to me. Okay. And I got to give a shout out to, and you know who you are, because you sent me the email highlighting this paper. And it's just kind of one of those things that's interesting when you're searching for things that block certain enzymes. We sometimes don't always get all that the literature has to offer, even with like repeated searches, and really trying to do deep dives. And this, funny enough, kind of like got off my radar from a couple different ways. So my point is that ivermectin is something that I have not covered at all on this channel, only not because I'm not open to exploring it and using it and other things, because I think there's a lot of things that it can do outside of the metabolic approach to cancer. But it came on my radar now because it is blocking multiple areas of glycolysis. And this paper was published in April of 2022, saying ivermectin accelerates autophagic death of glioma cells, or GBM cells, by inhibiting glycolysis through blocking GLUT4 mediated JAK-STAT signaling pathway activation. And I highlighted this in particular because it says ivermectin inhibited GLUT4 protein. So one of the glucose transporters is downregulated. Okay. It also, and overexpression of GLUT4 promoted glycolysis and inhibited autophagic cell death in these U87 cells. So basically what they found was that if the GLUT4 transporter was overexpressed, or it was highly upregulated, it would promote glycolysis, of course, because you're bringing a bunch of glucose in, and it would inhibit autophagic cell death in these glioma cells. But when they gave ivermectin, it actually blocked GLUT4 protein expression, and ivermectin inhibited glycolysis by blocking GLUT4 mediated it blocked GLUT4, which was mediating this Janus kinase signaling transducer and activating of transcription factor JAK-STAT and pathway. And it says later that ivermectin inhibited tumor growth in vivo, decreased the protein expression of GLUT4, JAK2, hexokinase 2, and why it popped on my radar for this particular video. I'd missed it for the GLUT transporter and the hexokinase videos, but I got it for the PFK video at least. So it decreases the amount of PFK available to these cancer cells, which is a major rate limiting enzyme of the glycolysis and Warburg effect and cancer metabolism as a whole. And although I couldn't get a cool graphic for ivermectin for cancer, I found this paper, and I only have the abstract here, so I give the credit to the authors who made this beautiful graphic. But I'm actually going to zoom in here. Let's try 75. That's not enough. Let's try 100. All right, so let's see if we can go through here. So ivermectin, according to this paper, is blocking PFKP, okay? So that's probably one of the more common isoforms of PFK, the PFK platelet type here, okay? So this is where ivermectin, anywhere you see a little capsule that looks like this, that means ivermectin is blocking it, okay? So we see a little X. It's also blocking the lactate transporters, which will decrease intracellular pH and cause all of glycolysis enzymes not to work adequately. It's like a secondary cool mechanism. It looks like it blocks complex 1 of the mitochondrial electron transport chain, which is why, and complex 3, which is why I probably wouldn't want to use it for preventive medicine or using it on a regular basis, because we're kind of inhibiting mitochondrial function. But this allows for what's left of the mitochondrial oxphos to be shut down, and for it likely to be leaky of electrons, which allows for the restoration of apoptosis through the caspase system. It also blocks a key enzyme in the Krebs cycle within the mitochondria as well. And again, this is a paper that was looked at for COVID-19. Can we say too little, too late? February of 2023. It ends up, the answer was it was effective. So my point is that this paper, this is probably the same authors or types of folks that were probably telling you were crazy for even considering it during that era, but I'll digress. But they did bring up a beautiful graphic for us to see, and you can see how this could be very effective potentially for cancer, looking at cancer as a metabolic disease, which is what I always try to look at the lens of. And now I have ivermectin on our list of things that can enhance the blockade of PFK. It's now firmly on here. I'm going to go ahead and make this question mark no longer. And we now have it. So this is the list of inhibitors that I was able to find that have an effect on PFK. So we have like ginseng, we have curcumin, we have resveratrol, oleanic acid, cardamom, berberine, EGCG, quercetin. Some of these other ones, I'm not really sure where they come from. I have to look it up and see where these come from. These saponins and stuff that come from. I did look up vitamin K3 and K5. They are synthetic vitamin Ks that are given to animals, and they seem to be toxic to humans. I only put these on here so in case you're looking through the literature and you're thinking, oh, I should get some of this for myself, I would highly, highly not recommend doing that. That sounds like a bad idea, but it does block PFK. Bumex or bumetanide is a diuretic, a powerful diuretic we use in the hospital. Clotrimazole, ivermectin, and aspirin. And, you know, I did have some more slides after the ivermectin paper, looking at, you know, this particular slide I wanted to show, for example, showing, you know, the paper that we have been looking at over and over again, showing the classes of kind of flavonoids and alkaloids and terpenes and stuff like that that are having effects on PFK kind of in vivo and in vitro. You see the study types and you see the type of cancers that were studied. But my point is that there's a lot of different options we have. I have further, I had another cool graphic looking at EGCG blocking PFK here, as well as a whole host of natural products, as a matter of fact, that block PFK and a variety of liver-related diseases. But we don't have a lot of time left. I've already gone an hour and 17 minutes. Here's resveratrol blocking PFK in a dose-dependent fashion as well. PFK activity in a dose-dependent fashion is lowered by increasing resveratrol concentrations. So my point is that I couldn't find cool graphics or graphs for every single one of these things because it just is not a well-studied, you know, there's just not a lot of fervor behind looking at natural products that block PFK in particular. we had seen a little more fervor for like GLUT transporters and hexokinase, but not PFK. And but I did want to give, at least as of Monday, April 28th, 2025, my gestalt slide on, things that have activity either down regulating or straight up blocking the activity of PFK. I will say that a lot of them, I couldn't tell exactly how the mechanisms worked. I just know that they did. But I know for a fact that EGCG as well as aspirin will, if you remember it from the aspirin talk, part of the talk, it separates the active enzyme into the two different subtypes or different molecules, the dimers that are inactive. EGCG did in that paper talk about that's its mechanism, so it has an effect similar to that of aspirin. But the rest of them either have an inhibitory effect or they actually will cause the protein to not be expressed or the gene not to be transcribed or whatnot. And there'll be a systematic downregulation. But ultimately, it allows not as much PFK to be around and not as much to be active and not as much to, allow the Warburg effect to be continued and for glycolysis to happen. All right, let's see if I got any comments here because I'm about to be done here. Let's see. I just met a woman with triple negative breast cancer. Does one route work better than another? Gave her your info. I'm not sure what you mean by does one route work better? What I would say is that even though we're talking about an enzyme one at a time, just so we can systematically look at the glycolysis system and the Warburg effect, I don't think that looking at one particular enzyme is a good idea. I think looking at systems is a better idea. So for example, like the major rate limiting enzymes, at least so far covered, has been the glucose transporters, has been hexokinase, has been this PFK, right? So one strategy I think could be like finding either one or a couple of different products that block all of those things, right? So like you'll see that curcumin like probably has an effect on all three of those things. So does probably resveratrol, so does berberine, so does EGCG, quercetin, et cetera, right? So like if you give quercetin or you give EGCG, you're likely blocking all three of those, just three enzymes that I just mentioned, part of the glycolysis system. Metformin also has diverse effects on the glucose system as well. But even then, even if you were to find a strategy of like drugs and or supplements that were able to block the key enzymes of glycolysis, it would still be added to the foundation of ketogenic metabolic therapy, right? As of, GKI of 1, glucose of less than 80, et cetera, right? That would be the foundation first. And I would say that that's probably the most difficult part, as always, of the therapy is getting that glucose down. What do you think about polyamine inhibitors like DFMO? I am not familiar with DFMO whatsoever, so therefore I'd have to look into that, Jesse. I'm not sure. Berberine, chromium, allulose. Taking thiamine has completely changed my life. Cool. In what way, Corey? I'm just wondering. Dr. Casey, greetings from the Netherlands. Well, greetings from Florida to you. Thiamine is vital for maintaining healthy and restoring vagus nerve oxidation. Yeah, so thiamine, we've talked about on this channel several times as being an inhibitor of PDK or pyruvate dehydrogenase kinase, as well as an activator of pyruvate dehydrogenase. It's one of the key cofactors of PDH. Of course, there's more to thiamine than just that, but within cancer in particular, that is critical for the metabolic reprogramming. Does acetogenins inhibit NADH dehydrogenase? I'm not familiar with that compound. I don't know the answer to that. I have to look into that. Greetings from Brazil. Greetings from Florida. Thank you for your noble work. My wife was diagnosed with stage 4 breast cancer 5 years ago, and we're told to get her things in order. Yeah, that's a horrible thing to hear. They gave her less than 1 year survival estimate. And she's here 5 years later. What did she do, Nelson, to get to live in 5 years after telling to get her affairs in order? 600 milligrams every 8 hours is a lot. What is the toxicity data on this? Well, what I would say is that I have personally used high dose of aspirin like that for, not that pericarditis is a very common thing in the hospital, but I've seen it used, and that's the standard dosing. It's just not given forever, right? It is a high dose, and I think that there's going to be plenty of people out there that there'd be contraindications to them. If they have any kind of like gastritis, ulcers, if they have renal dysfunction, if they are on any like other antiplatelets like Plavix or Eliquis, Xarelto, Pradaxa, warfarin, et cetera, the actual anticoagulants, that would be probably a big no-no of high-dose aspirin. The question is, do we even need high-dose aspirin? The question is, how much aspirin does it take to get to the millimolar quantities in the bloodstream that was seen in these studies, right? That's the next question that I don't know the answer to yet, but I need to find that answer out. What kind of aspirin dosage were they using? Can't be very much because of the blood thinning. You'd be surprised. We actually, like I was saying, we actually use pretty high dose of aspirin for certain conditions, such as pericarditis. You're a legend in these videos. I appreciate being given legend status. The chemo business is worth billions. Yeah, I know. Ivermectin. LOL. Post-COVID dysautonomia is a good umbrella term for what I went through. Thiamine, along with other nutrients, are slowly giving me my life back. I've been 3 to 4 years of my health falling apart. Corey, I'm really sorry to hear about your health falling apart. I'm so glad that you've had good effects from thiamine. One of my mentors, Dr. Jack Cruz, talks about, long COVID and it's like that being a mitochondrial issue. And so it would make sense that certain nutrients and thiamine would help bolster your mitochondrial function. But I would not limit my strategies to just giving, nutrients that are necessary for mitochondria to function well. I would look at strategies at reversing mitochondrial heteroplasmy. I have videos on it. And I would look at ways of enhancing mitophagy as well as mitochondrial biogenesis. Spark in the dark, 1, 2, 3. Acetogenins is a group of compounds in soursop leaves. Interesting. So I can't say I've ever used clinically or even personally soursop leaves, but my wife is Colombian, and when I go to Colombia, I always try to eat soursop. It's also known as guanábana in Colombia, and it is unbelievable good. It is not a ketogenic food by all means, so it's not something you'd want to probably do on a ketogenic metabolic therapy. If you're healthy and you're down in the tropics, it is a fantastic fruit, though. That being said, very, very tasty. They make juices out of it, you name it. So no, I'm not familiar with that compound in the soursop leaves, but if it's similar to like an apigenin or like one of those flavonoids, I would have to guess it probably has very similar properties to those other flavonoids, and therefore it probably has multifactorial effects on cancer's metabolism. Corey says, 100%, just came across your info, really excited to dive in more. Ended up in a strange state where my body kept pushing into ketosis, blood sugar roller coaster of POTS. Man, that sounds really horrible. That sounds horrible. Yeah, I see POTS. I can see that being part of the autonomic dysfunction. Well, look, man, I hope that you get on track. It sounds like you're already back on track. Probably the medical system gave you no help whatsoever. I would look into Dr. Cruz and, just be aware that he's like up here and he's also pretty abrasive. But if you can get past that, he is brilliant and he can probably help you. And I would really look into his stuff as a foundational principle of how to improve your mitochondria. Yeah. So Natal is asking about mebendazole, when to take it, et cetera. So I have a pretty strong, code that I don't really give dosages and dosing strategies on the YouTube channel, just because that's kind of like practicing clinical medicine. And so I don't think it's responsible. What I would say is that the dosing strategies used are readily available in some of the glioblastoma studies. And I can tell you they went from anywhere from 10 on the low end to 200 milligrams per kilogram. And it was generally in divided doses throughout the day in general, with a fat-containing meal. That's what they use in the studies. So you can use your best judgment, or better to work with a doctor who knows what they're doing using mebendazole. Nope, medical system made me worse. If anything, many ER visits, saline was what I got most. I was in ketoacidosis, according to my blood work, multiple times. Have wondered if that was starvation state. Could be. It depends on the level of ketosis. Ketosis is not ketoacidosis. Ketosis is normal physiologic condition if you're either fasted or in a high fat diet, right? Ketoacidosis is when you actually drop your blood pH, right? That's like a pathologic condition, and it's not generally seen with starvation states. I happen to see this a lot because I work in the hospital, and just something as simple as a basic or a comprehensive metabolic panel will tell you the acid base status, at least in general. And if I see a gap acidosis, I'll check BHB, and if BHB is elevated, it's going to be like a profound elevation. It's usually pathologic in like this in like an alcoholic or a diabetic ketoacidosis. So I would be very surprised if you had true ketoacidosis from being in a starvation state. But that's what they call basically pseudohypoxia, right? Like you're breaking down fat and you can't get it into the mitochondria, probably because probably from thymine, a thymine issue. So your mitochondria are shot. So this is why my gap was high, 17, CO2 is low. Yeah. I mean, the gap is high. That's quite no question. 10 plus or minus 2 would be normal, right? So that is a high gap. CO2 is low. It's not super low. 21 is generally low in a normal. So it's not like a super, super low. But yeah, I mean, I would have looked for other causes, to be very frank with you, if you were my patient, for the reason for your anion gap acidosis, besides just starvation. Cause I think that, again, I've seen many starvation ketoses, and they don't generally cause that high of a gap and a low CO2. Spreading aspirin throughout the day better. I don't know the answer to it. I don't know the answer to the dosing strategies for aspirin yet, because we got to figure out how much it takes to actually get the millimolar concentrations, and then see how long that lasts in the bloodstream and see what you need to do. I would hope it would not be high doses, because I think that you start playing with fire at that point. GPT suggests DFMO to go along with metabolic therapy. It looks very promising in my amateur opinion. Well, your amateur opinion, is probably more than most oncologists have an opinion on. They'll just tell you there's nothing to do with glucose. So I would say that it needs to be looked into. I'll have to look into it. And can you make a video on propolis? It seems to be a very natural way to treat apoptosis. So this is a great segue into the end of the video. So I'm not against doing a video on propolis, number one. But number two is that you can get into the weeds pretty easily of, apoptosis is triggered by X, Y, and Z, right? But I always want to refocus us back on, does propolis or green propolis have an effect on glucose and glutamine first and foremost? And then if we want to add other stuff like propolis or, DMFSO or whatever, DFMO, as an additive, then maybe, right? But I always want to refocus us on glucose and glutamine. So if I do study propolis and I do a video on it, it'll be on its perspective of, does it have an effect on glucose and glutamine first and foremost, and then we can look at other things that it can do. All right, guys, I cannot believe I've got an hour and a half, but it was a important topic, and I'm glad that I was able to, share what I was able to find. And then the next video we have will be on the next enzyme in question, which will be a PFK-FB, which we did touch on a little bit during this video, but I want to do its due justice, I guess you'd call it, and looking at things that can potentially block it so that we can give anybody who's listening to this a better shot at outliving the odds that is given by the conventional medical people. If you like videos like this, please like it. If you're not a subscriber, you're not a mitochondriac, please join our channel. It is free. And if you have anybody in your life, whether it be your loved one, whether it be a friend, whether it be an acquaintance or a stranger that could use this information, if it could benefit them and their health in some way, shape, or form, please share it with them. And until next time.